In this podcast, we will talk about writing formulas for ionic compounds, and we're going to talk about what that looks like and how that's different for both representative metals and transition metals in ionic compounds. All right, let's learn how to write formulas for ionic compounds. When we are working with ionic compounds with representative metals, our group A metals, the metal symbol is always written first and your non-metal is always written second. Okay, so we will convert the name to the symbol, and then we also, I think it's good practice just to stick the charge on there as you go. Okay, and so we're going to look at those charges and we're going to determine how to get a sum of 0. I like to do a special method that I call the drop and swap, and I'll show you that in just a moment. But we put the subscript after the element, and the subscript is going to denote how many of something we have. So for example, if we have element X and it has a charge of 1, and we have element Y with a charge of -2, okay, we're going to drop and swap. We're going to bring the 2 down to become the subscript for X, and the 1 comes down to become the subscript for Y, giving us X2, Y. We don't write 1, we're chemists. We figure if you've written the elements, there's at least one of them. Okay, so that is the drop. So grab those charges and bring them down to subscript. You're going to drop and swap. Also a cool dance move. You're welcome. One thing to just double check is that the sum of your charges is equal to 0. And we're going to keep practicing that. You have to have a neutral compound. All of your positive charges have to add up, be opposite but equal to all of your negative charges. And we do not write any charges in the formula, ever, never. So let's take a look at our example. We were given sodium iodide, so we first write the symbol and the charge, and iodide is iodine. Sounds funny to me, with a -1 charge. So we have the charges set up, and we are going to drop and swap. Notice that we don't have the number 1 written here. 2 reasons. First of all, we never write the number 1. Second of all, those would be reduced and you wouldn't have to put those, and we'll see what that looks like later. But again, +1 charge on sodium and a -1 charge on sodium on iodine equals 0. We can also think about this in terms of the electrons. So sodium has 1 valence electron, iodine has 7. The metal transfers an electron to the non-metal. Okay, if we lose 1 negative charge, we have a +1 charge. If we gain 1 negative charge or 1 electron, we have a -1 charge. So that's where those charges are coming from. So another way to think about this, I'm a very visual person, so let's think about aluminum and let's think about oxygen. Looking at our periodic table, aluminum is a metal in group 3A, so it has a +3 charge. Oxygen is a nonmetal and it has a -2 charge. Okay, so when I'm making an ionic bond, the sum of the charges always has to add up to 0. It has to be neutral. So I have to get a little bit creative with how many aluminums or oxygens I have and what the proportions are for those to cancel them out. So if I were to have these in a 1-to-1 ratio, that wouldn't work. Instead, I want you to think about this image over here with the Legos. Okay, the first number +3 and -2 has in common is 6. Okay, so I'm actually going to need a total of 6 positive charges and a total of 6 negative charges for this sum to be 0. Okay, so that means I'm going to need 2 aluminums for every 3 oxygens. So that's what we see with our Legos. You have 3 red blocks for the oxygens for every 2 of the blue blocks of aluminum. Looking at this yet another way, and we're going to practice this a lot. To determine what the ratio is, we can drop and swap these as well. So we need 2 aluminums for every 3 oxygen. Okay. Mathematically, that's 2 times positive 3 gives me positive 6, and that's 3 times negative 2 gives me negative 6. I can always double check my work. And again, we're going to go into more of this, but I want you to think about this idea that the charges have to add up to numbers. The positive charges have to cancel out the negative charges. And what is the proportion or the ratio of these that we need to have to each other? Let's do some examples. All right, I can tell that these are all representative metals because there's no Roman numerals showing us what the charge is for those transition metals. So let's work through these. First thing we're going to do, we are going to convert the names to their chemical symbols from the periodic table. So lithium is Li, and it is a group 1A element, which means it has a +1 charge. Oxide is oxygen. Looking at the periodic table, that's a nonmetal with a 2- charge. All right, so next step is to do that fun drop and swap. So we're going to take charges, and we're going to swap them down to the subscripts of the opposite element. Boom, boom. What I get is Li2O. To double check our work, let's look at this mathematically. Go through these steps until you're confident you know what you're doing. I have 2 lithiums. They have a +1 charge. That is an overall charge of +2. I have 1 oxygen. Notice I didn't write the number there because we're chemists. We try not to write more than we absolutely have to. That has a -2 charge. 1 times -2 is -2. Adding those up, boom, 0. The drop and swap system works. Let's move on. Calcium sulfide. Looking at my periodic table, calcium is Ca. It is a group 2A representative metal, +2 charge. And sulfide is sulfur, also has a -2 charge. So again, now that we've written the symbol with the charge, we're going to drop and swap. Okay. So we wind up with Ca2S2. Wait a second. 2 to 2 is the same as 1 to 1. That's not the lowest ratio possible. I could divide both of those by 2. Because they're opposite but equal, we consider that a 1-to-1 ratio, and you would just write CAS. Now you only reduce for ionic compounds. Okay, that can be representative metals, transition metals, but if these are the same number, reduce them. Okay, we want the lowest ratio. All right, next example, magnesium. Looking on my periodic table, that's Mg with a 2+ charge. Fluoride is fluorine with a -1 charge. We have the symbols, we have the charges, we're ready to drop and swap. Let's do it. Okay, so we have Mg, 1 Mg, I'm not going to write the 1, and we have 2 fluorines. One thing I didn't do on the last one, but we'll just do it here, is I did not double check my charges. So I have 1 magnesium with a 2+ charge. So 1 times +2 is +2. I have 2 fluorines with a -1 charge. 2 times -1 is -2. That cancels out. Perfect. I know I've done this right. Next, we're going to talk about writing formulas with transition metals. So the rules are all the same, thankfully, as what we did for the representative metals, except you will get a name that has a number in Roman numerals. So here's your Roman numerals. There's our number. And the charge is denoted by the Roman numerals. So for instance, iron 2 would be iron with a +2 charge. Let's practice writing formulas. All right, so the only difference between the representative metals and the transition metals and ionic compounds is the presence of these Roman numerals. And it's actually really nice because when there's a Roman numeral there, I don't have to go to the periodic table to look up the charge. It's just given right there. All right, so iron is Fe. I'm told by my Roman numeral that it has a +2 charge. Chlorine, looking at the periodic table, is Cl with a 1- charge. The rules are the same. I've written the charges, I've written the symbols, so the next thing to do is to take those charges, drop and swap them to the subscript of the opposite element. So this would be Fe1Cl2. Notice that I'm not writing that. And I'm going to double check my math on this. I have one iron with a +2 charge. 1 times +2 is +2. And I have 2 chlorine with a -1 charge. 2 times -1 is -2. And that adds up to 0. You can always double check your work to make sure that you have the right ratio of negative charges to positive charges. All right, moving down the line. Copper 2 sulfide. Looking at the periodic table, copper is Cu. I don't have to look at the periodic table for the charge because the Roman numeral tells me it's +2. Sulfide is sulfur. Looking at the periodic table, it's a -2 charge. Next step, drop and swap. So this is Cu2S2. Wait a second, both of these could be divided by 2. That's a 1-to-1 ratio. So I'm actually going to write this as Cus. Now, you might be tempted, McCann, Jewel, Gabbard, whatever, whomever, you might be tempted to say, well, wait a second, couldn't I just reverse the subscript and find the charge? No, don't do it. Don't be tempted to do it. The math isn't going to work out, and here's why. If I were to reverse what was there, okay, I would think that I have copper 1 and that sulfur has a -1 charge. Don't do it. Always go to the math. Always check the charges and double check that they're canceling to 0, and that's because we reduce. Never reverse a drop and swap. It's one direction, one way. Do not enter. All right, next example is tin 4, that is 4, bromide. So tin is Sn, because of course it is, with a 4+ charge. I know it's a +4 charge because it's given to me right there in the Roman numerals. It's fantastic. Bromide is bromine, Br, with a -1 charge. Okay, we have the symbol, we have the charge. We're ready for the drop and swap. Let's do it. I get Sn. I'm not going to write the 1 because chemists are kind of lazy about the writing. Br4. Let's double check. We have 4 -1 charges, and we have 1 tin, which I'm told has a +4 charge. Those are opposite but equal, and they cancel. I've done everything correctly. All right, here's an example of more ionic compounds in your everyday life. Sunscreen. I know there is a big push lately for a mineral-based sunscreen as opposed to a chemical-based sunscreen. I'm going to tell you right now, if you're wearing sunscreen, you're doing a great job. Okay, so a lot of sunscreens have ingredients, the natural ones, the mineral blocks or the physical block, will have something called zinc oxide. So let's take a look. Zinc is Zn. We know this has a +2 charge. Oxygen has a -2, opposite but equal. So a lot of them have zinc oxide crystals. And these zinc oxide crystals actually reflect the sunlight away from the skin, and that's how they protect the skin from sun exposure. It's more of a reflection. It's a physical barrier rather than a chemical barrier. Kind of neat.